In this video, we'll be doing a second proof by mathematical induction. This time, we want to show that 1 plus 3 plus 3 squared plus 3 to the n minus 1 is equal to 3 to the n minus 1 divided by 2. We start our proof by showing that s sub 1 is true. For s sub 1, we're simply replacing the n in 3n minus 1 over 2 with 1, and we want to see, do we get the number 1, which is the first number in our sequence. Three to the first minus 1 over 2. It's going to be 3 minus 1 over 2, which is indeed equal to 1. If that wasn't true, we'd just stop right there and state that this could not be proved by mathematical induction. Next, we want to assume s sub k is true. That means that we will be assuming that s sub k, which is equal to 1 plus 3 squared plus 3 to the k minus 1 is equal to 3 to the k minus 1 all over 2. So here, all we did was replace the n's in our original statement with a k. Now that we have assumed that our statement is true for the kth term, we need to show that s sub k plus 1 is also true. That means that we should show that s sub k plus 1, which is equal to 1 plus 3 squared plus 3 to the k minus 1 plus 3 to the k plus 1 minus 1 is equal to 3 to the k plus 1 minus 1 divided by 2. Starting with s sub k plus 1, this is equal to 1 plus 3 squared plus 3 to the k minus 1 plus 3, and I'm going to clean up that exponent and just make it k. In our assumption line above, we said that 1 plus 3 squared plus 3 to the k minus 1 was equal to 3 to the k minus 1 divided by 2, and that's what we have down here. So we're going to substitute this here, this s sub k, for 3 to the k minus 1 divided by 2. And then we still have this plus 3 to the k. We want to add these together. We'll need a common denominator. So I'll throw this over 1, and then we'll multiply top and bottom by 2. 3 to the k minus 1 over 2. Now be careful when you write this. 3 to the k times 2 does not become 6 to the k. Okay? We cannot multiply bases together when we have an exponent on it. So the 2 just goes hanging out in front. And I always use a dot to indicate that we're multiplying here so I don't mistake it for 23. Now that we have our common denominator, we can add our numerators together. Put it over our common denominator. We want to simplify our numerator because think about what we're trying to show. We're trying to get back up to here. So we want to simplify our numerator until we get there. Well, notice that we have this 3 to the k, and then we have 2 times 3 to the k. These are actually like terms. If I have 1 3 to the k and I want to add 2 3 to the k's, we end up with 3 3 to the k's. Well, we're getting closer to the green box, right? We have the -1 and the over 2. It's that 3 to the k plus 1 that we don't have quite yet. Well, I have 3 times 3 to the k. This standalone 3 is actually 3 to the first. We can now use exponent rules to combine these. See, we have the same base. They're both 3. So we can add our exponents and put that sum as the exponent on a single base. This turns into 3 to the k plus 1 minus 1 over 2. And notice that was what we were trying to get to. So we have shown that this is a true statement. We now just need to write our wrap-up proof statement. Therefore, by mathematical induction, one plus 3 squared plus 3 to the n minus 1 is equal to 3 to the n minus 1 divided by 2 for all positive integers n. All of these induction proofs really follow the exact same pattern. If we look back, we show that the first one is true by simply plugging 1 into our formula and making sure we get the first term in the sequence. Then we assume that S sub k is true. And what that means is simply plug k into our original statement for n. Next, we want to show that S sub k plus 1 is true. So here, all we're doing is putting k plus 1 in for n. Next, we take almost the whole beginning and substitute what we assumed S sub k was in for that. Then we just have to add the next 2 terms and clean it up until we get what we said we were going to show in the first place. So after you do several of these, you're going to see it really follows the same pattern over and over again.